looking a little more, bit more at Clausius-Clapeyron, here is the relation I already mentioned in the first podcast, and you can see here I fixed the subscripts. So let's look at this relation and see what it means in the context of the temperature gradients, etc. in the atmosphere. These latent heat of evaporation and sublimation actually do vary with temperature, but if for simplicity we assume that they are independent of temperature, then we can integrate this relation for going from temperature T1 to T2, which is fairly straightforward if you know how to do this. T is constant, so it doesn't do much, whereas epsilon is going to give us the E of S is going to give us the exponential. So exponential of temperature T2 is going to be water vapor pressure at T1 times the exponential of the latent heat. So we keep both of them here because it just depends on the transition you are making, whether you are going between evaporation and condensation or sublimation and deposition, right? And that's the ideal gas constant for water vapor, and it's going to depend on 1 over T2 minus 1 over T1 just by integrating this equation. What is it good for? Obviously it tells you, we will see how the body force for moving energy from the tropics to high latitudes is created. We have approximately already said that the Earth being a sphere creates energy excess in the low latitudes in terms of the shortwave energy coming in and the long wave energy going out, and there is an energy deficit at polar latitudes where there is less solar energy coming in than long wave energy being lost to space. And if you have energy deficit, then the place will keep getting colder and colder. If you have energy surplus, it'll keep getting warmer and warmer unless you move the energy from the surplus region to the deficit region, which is what gives us weather and climate. But what is the force that makes things move? We can think of it as a body force that's created by processes like this, where you have warmer temperatures in the tropics and then the gradient decreasing temperature towards the poles. So for that reason you can look at the warmer and colder columns of air, let's say, next to each other, and see how that creates water vapor gradients and then what it results in terms of the heating in the atmosphere. Okay, so looking at the phase diagram of water, we are looking here at temperature and partial pressure of water vapor. You have seen this probably somewhere in high school basic physics and chemistry. We have the temperature range below 273 degree Kelvin. Remember, this is Kelvin here, where you have equilibrium along this line between water vapor and solid. So that's essentially the sublimation process that we talked about. And on this side, in this temperature range and this partial pressure water vapor, you're going to have solid and you're going to have vapor here, and this is the line along which you can have liquid and vapor be in equilibrium. And here we are at 100 degrees centigrade or 373 Kelvin, where you reach the standard boiling point, and this is the standard melting point of going from solid to liquid. So those are the three latent heats of exchanges between the phases, and this diagram has been used to also conjecture about the way planets would have evolved after the solar system got formed. So this is critical to just off the bat establish why water vapor is a key player in Earth's weather and climate at all time scales. So start on this temperature scale and imagine the solar system just got formed. The continents over the Earth have not formed yet. It's a primordial soup with meteorites crashing, lots of volcanic activity, no life as of then that we can find evidence for, and the partial pressure of water vapor begins to increase, and Mars, because of its mean temperature being minus 50 degrees at present, it would have been something at that time, remembering that Sun itself was 30% less luminous when it got formed. That's called the faint young sun paradox, which has to be explained in terms of how water would have been in liquid form, because as far as we know, there is evidence that water was in liquid form from the beginning, and then there are issues of how life would have survived till Sun reached the present level of energy, reaching the Earth and so on. So Mars would have hit this phase line here in terms of the partial pressure of water vapor and temperature, so it would remain in this solid and vapor phase combination. So as far as we know, Mars has probably frozen water, and the atmosphere has some water vapor, but we cannot find at present any evidence for liquid water on the surface. Various features have been interpreted as water flowing in the past, which have to be explained and so on. And Earth, on the other hand, evolved non-linearly and started at some temperature here below 273, and as it got warmer, as continents began to form, the volcanic activity subsided, etc. You non-linearly reached this point here where we are now, because Earth has liquid, solid, and water vapor in the system. We have glaciers and sea ice. We have, of course, lots of liquid as oceans, lakes, soil moisture, etc. And we have water vapor, plenty of it in the atmosphere, especially at warmer temperatures. On the other hand, Venus, which started out warm here, went off parallel to this phase line here of liquid and water vapor. This is kind of a heuristic hypothesis that has been around for a while, and I didn't read all the caption here, but you can see what the arguments are like for where we are now. So if you just think about the temperature of Mars at minus 50 degrees at the surface, 50 degrees centigrade at the surface, Earth, the average temperature of global mean temperature of 15 degrees centigrade, and Venus at 460 degrees centigrade. You have to put that in the context of the amount of energy received from the Sun. Take the distance, the flux of the Sun drops off as 1 over r squared, where r is the distance from the Sun, and then you have to explain the temperatures in terms of energy balance. So the runaway warming on Venus can be explained in terms of the energy it received and it receives, and the greenhouse warming effect it has, whereas Mars doesn't receive that much less energy than Earth, but its runaway cooling has settled into an equilibrium of minus 50 degrees centigrade, whereas Earth has the so-called Goldilocks blanket greenhouse effect, which gives us this existence at the triple point with a mild 15 degrees centigrade average temperature. Obviously, we will look at the energy balance to explain these energy balance on Earth to see where the energy is going from the energy that is received from the Sun, and how it is balanced in the system, and what the greenhouse effect does in terms of the atmospheric temperature, surface temperature, emission temperature, and so on. That is a critical part of this hydrologic and heat exchanges. Okay, so there is the global mean energy balance to explain the global mean temperature, and then we have to explain the variability within that at all these timescales that we looked at, synoptic timescale, subseasonal timescale, interannual to decadal and longer timescales.